to kind of think this through. If there was no gravity, when the monkey lets go, he's just hanging there. And if you were firing a bullet, the bullet would travel along this line. Does that make sense? Now, the bullet and the monkey, if they start to experience maybe a little bit of gravity, the monkey will fall a little bit, but there'll also be an acceleration on the bullet, which will cause the bullet to fall a little bit. What this example is supposed to illustrate is that the time in which the monkey falls is going to produce a displacement for the monkey due to the acceleration it experiences. The bullet is experiencing the exact same acceleration. And because it's experiencing the same acceleration, it's going to fall below the path that it would have traveled on had it been not experiencing acceleration. So it's not falling, but it's falling beneath the path it would have traveled on because it's experiencing the same acceleration for the same period of time. Now, if you don't understand why that works the way it does, just look at the motion equation that would be a part of that. The only difference between the monkey and the bullet is the bullet has some initial velocity. But both the monkey and the bullet experience the exact same change due to the acceleration. If that were 0, the bullet would have traveled along this path, the one from its initial velocity. But it has to fall the same amount below that path as the monkey falls below that path. That's why they both have to strike the same place. So we're going to be doing a discussion on projectile motion. And I need you to become proficient. I'd like you to be in a position where you could probably predict this. Now, there is a case where we don't hit the monkey. And I don't know if you would imagine this case, but the case where you don't hit the monkey is when you shoot with so little velocity that you hit the ground before the monkey. That clearly there is a possibility that you won't hit the monkey. That's because you think the monkey might tunnel into the ground and you'll hit it down there. So the ground can get in the way. So when we talk about projectile, I want to I'm going to say ease us into it. It's an object that's going to move in 2 dimensions while experiencing an acceleration in 1. So we're going to start with a basic problem, one that's mathematically simple to solve. And then we're going to move to a more advanced problem where we're going to add trig to it. But we're going to make a change to the problem to make it just as simple to solve, just now having a little trig. And then we're going to do the advanced problem where there's no holds barred and you have trig and a full problem. So we're going to kind of step our way through from a simple problem to a more advanced problem. And so to understand the simple problem, I want you to consider just rolling an object off of your desk. So I'm going to kind of draw a desk or a table, and we're going to take an object and roll it off the table. Now, in drawing this, what I'm trying to indicate is that the object, as it rolls across your tabletop, has a velocity already. And I don't think there's a person here who doesn't believe that once it leaves the table, it's going to travel on some kind of curved path. No, this is not the curved path it would travel. This is circular more than anything else. When we talk about what the path actually is, we'll try and do some work to see what the path is supposed to look like. The path of a projectile is called its trajectory. That's the path of a projectile. It's called the trajectory. And so we'll talk about what trajectories look like, but it's the path or the actual place in which the object is in space. But for right now, we're going to kind of ignore the trajectory and just talk about what the ball does when it's moving through space. The moment it leaves the table, we know it's going to travel along a path like this. The definition of a projectile is an object that moves in 2 dimensions but only experiences an acceleration in 1. The acceleration is that due to gravity, which means this object's horizontal velocity doesn't ever change. The horizontal velocity isn't experiencing an acceleration, as long as we make the caveat that there's no air resistance, which right now we're playing in magic fantasy physics land where there's no air resistance. So whatever this is for a horizontal velocity, that stays the same for all projectiles. All projectiles have a constant horizontal velocity. However, if it's rolling along the table, we know that while it's on the table, it's supported, and it has no vertical velocity. But the moment it's over open air, gravity can act to pull it downwards. And the longer it's in the air, the more gravity can change its vertical velocity. So a projectile is going to have horizontal information or horizontal components, and it's going to have vertical components. So for a projectile, we're going to refer to the horizontal parts as being with a subscript of x, and the vertical parts are going to have a subscript of y, so that we have a way of keeping track of them separately. Now, truthfully, the object has one velocity, the resultant. We're breaking it up into components, but at any one time, the object has one velocity. We study the components because that's where gravity is acting, on one component and not another. But it always has some resultant velocity, something we'll just call v. And that's clearly getting to be a bigger and bigger number all the time. But the horizontal part isn't changing. It's the vertical part that's changing. So I've emphasized that a lot because what we're going to have to do then is take all of our problems and break them up into two parts. A vertical part and a horizontal part. The vertical part is the part that's going to experience an acceleration. So it's going to have in it all of the things we've come to expect for an object experiencing an acceleration. Right? 5 motion variables. An initial velocity, a final velocity, an acceleration, a displacement, and time. The horizontal part, though, has no acceleration, which means the vertical part only has information related to an object traveling at a constant speed. So there's no initial and final velocity, there's just velocity. There's no acceleration because it's not changing its velocity, so all we have is time. The thing that you have to come to grips with is that the time that it takes the object to fall is the same as the time it takes the object to move sideways. In a projectile problem, we link the two sides together with time. In fact, in any projectile problem, we're going to be looking to see if we have enough information to get the time in the vertical side, or do we have enough information to get the time in the horizontal side. There has to be enough information for us to get the time. Now, projectile problems are solved by figuring out how long the projectile is in the air. So generally, the thing we're usually interested in is what's called the range. The range of a projectile is its horizontal displacement. It's the distance from where it was launched to where it lands. Delta y, that's a measure generally of how high or low the object is from where it started. So if you roll something off your desk, the object's going to have probably a negative delta y because it lands on the floor. You try to shoot a basket to the hoop, it's going to have a positive delta y because it's going to land higher than where it started. So delta y is the vertical displacement, but the distance from where you shoot the ball to where the basket is the horizontal range. Is that somebody just really hungry? Or
I'm pretty hungry.
because that sounds very directional.
Yeah, it sounds weird.
And generally when we hear thunder, we hear it through the windows because they're less insulated than the wall. So it just sounds unusual to me. I mean, I've been in this room for a lot of years and it just sounds unusual. All right, so a standard projectile problem. We don't have enough time to get into it because I think the bell is going to ring for you guys to go to lunch. Like what now? Is that true? How many minutes?
One.
Then yeah, we'll probably have to end here then.